Welcome to NASA headquarters in Washington. We are less than 3 weeks away from launching a pair of Earth-orbiting spacecraft that are literally going to take on the weight of the world. It's the GRACE follow-on mission, or GRACE-FO. Take a look.
Water is one of the main indicators of how the planet is responding to our evolving climate. We built our civilization around the climate that we had and the water resources that we had. And if those are changing, that can have a profound impact on how we operate our society.
GRACE and GRACE follow-on measure the motion of water around the Earth, and they measure that in all forms of water. Water that's stored underground, water in the ocean, water that's frozen in the form of glaciers. So all of that together, GRACE can measure.
GRACE follow-on is a mission to measure how water is distributed on the planet and how that changes from month to month.
GRACE stands for Gravity, Recovery, and Climate Experiment.
And it's a follow-on mission to this mission called GRACE that we launched in 2002. And that mission just ended a few months ago, and GRACE follow-on is going to pick up and continue that science legacy.
So even though GRACE flew for 15 years, climate is one of those things which takes place on decadal timescales. It's really important that we look at these trends over longer time periods so we can establish the forces which are driving them.
One follows the other, and between them they accurately track the distance between the two satellites. And as they fly over changes in mass on the Earth, they move back and forth. And we track those little changes very accurately. And we do that with global positioning system satellite information and with star cameras that are on board the two spacecraft. I think there's an increasing awareness and consciousness around the Earth that water is a critical resource, and that the sea level is rising, the polar caps are melting, and that all these have long-term ramifications on how we live.
The GRACE follow-on measurements give us very clear and tangible information so we can make sound decisions in the future of how we manage our resources.
Hi, I'm Karen Fox, and welcome to this NASA media briefing on our next Earth-observing mission, GRACE follow-on. GRACE stands for the Gravity, Recovery, and Climate Experiment. It's a joint mission between NASA and Germany. GRACE follow-on will carry on from a former mission, GRACE, together a unique data record that tracks our planet's water cycle, ice sheets, and more. Our briefing is in two parts today. First, we'll look at the amazing science that the mission will enable and how that will benefit people around the world. Then we'll switch to talking about the twin spacecraft themselves and how launch preparations are progressing in California. After each part, we'll be taking questions from the press, both here and on the phone. And if you're watching on NASA TV, you can ask questions too. Just post it on social media during the briefing with the hashtag AskNASA. Let's get started. First up, the science. We have three experts here today. In our studio is Michael Watkins, the GRACE follow-on science lead and director of NASA's Jet Propulsion Laboratory. Frank Webb, the GRACE follow-on project scientist at JPL. And joining us via Skype from Oberpfaffenhofen, Germany, is Frank Flexner, the GRACE follow-on project manager at the German Research Center for Geosciences, also known as GFZ, which is NASA's primary mission partner. We're going to start with the basics. Michael, tell me about GRACE follow-on and also its predecessor, GRACE. What did they do?
Well, thanks, Karen. It's a pleasure to be here. So GRACE and GRACE follow-on are some of NASA's most unique missions. So what GRACE has done and what GRACE follow-on will do shortly after its launch is map the Earth's water in motion. Now, what's fascinating about GRACE is it does it not by looking at the surface of the Earth, not by looking at water or bouncing a radar off the water, but by actually measuring the weight of the water. So it actually is able to tell how much water is in a given location on the Earth and how that's changing over time. And what GRACE was able to observe from that is because water takes many different forms. Sometimes it's in the form of groundwater, deep underground. Sometimes it's in the form of polar ice caps. Sometimes it could be in the form of ocean water moving around. Winds and ocean circulation can pile water up in more in one place and in another place. And GRACE observes all of that complete water cycle of the Earth and how it changes over time. And it's very unique in that sense because it measures water in all forms, and because it does it with this bathroom scale methodology by actually weighing the weight of the water as it moves around the Earth.
So we've had 15 years now of this kind of data that you're talking about. What has GRACE told us about the Earth that we didn't know before?
So let's take a look at this graphic. So as you said, we have 15 years of GRACE data. And what GRACE has shown us is there's significant changes in every part of the world and how much water is stored in each part of the world. Now, one of the unique things about this plot is that you notice GRACE has measurements of everywhere in the world, everywhere on land, in fact, a little bit in the oceans as well. And what you can see is sometimes that, again, that's ice sheets that have changed. Sometimes it's aquifer storage. But almost every part of the world has been observed by GRACE and has a story to tell. And that's actually resulted in GRACE coming up with some of the most scientific findings, most scientific publications of any mission in recent years in earth science, because it's just so broad in what it can tell us about the Earth. So if we take a look at this here, this is the average trend that GRACE has seen over the 15 years that it was in orbit from 2002 through 2017. The biggest signals are actually up in the poles. So the areas that are reddish in color are areas where water mass has gone away from those regions. And so the areas that have the most water mass loss are actually in Greenland, for example. You see all the red colors there in Greenland. That's actually ice that's melted off the Greenland ice caps. And you can see the same thing over in Alaska and down in the West Antarctic Peninsula. And so those have been contributing a significant amount. About 1/3 of sea level rise that we observe comes from polar ice melting that GRACE has observed. And it was actually not well known before we launched GRACE. It was not clear how much that was contributing to sea level and how much the ice sheets were changing. But it's also fascinating that you see a lot of blobs of green and red that, of course, are not ice. And that's areas where it's either been a drought and folks have been using groundwater, pumping groundwater for agriculture, for human use, for other purposes, for irrigation. In other cases, we have green areas where it's been heavy rain. It's been flooded even in some cases. So we all know some years, sometimes you have a couple of years that are dry and a couple of years that are wet. What you can't always tell is how did that water get deep into the earth? You know, if it was a drought, did I just lose water from the surface or did I lose it very deep down? And what do I do about replenishing that? And can I observe it being replenished when we have wetter years? So if you look at the areas that are greenish, those tend to be areas where it's been heavy rainfall and replenished. Areas where it's red are areas where there's been significant drought and use of fairly precious groundwater. And some of these areas are here in the United States, the Texas drought in California. Some of them are in parts of the developing world where the infrastructure may not be able to respond as quickly to those droughts and loss of groundwater. So this is very important data, and it's very important to how we understand our home planet and how it's changing.
Thank you very much. Frank, I'm going to ask you to do a deeper dive into some of these areas that Michael has been telling us about. Let's start off with the global water cycle. Tell us what it is and how GRACE follow-on scientists do it.
So the water and the water cycle play an important role in the Earth system. You know, water, it's necessary for sustaining life. It's an important media for transporting, heat on the planet, and it's a vital resource for our civilization. Now, in these charts, these next charts are just going to illustrate that, water comes in many forms to us. It's like rain, falls as rain, it falls as snow, it's surface water in rivers and lakes. It's also, locked up as frozen water and ice sheets, as well as water in the ground that we pump out for irrigation and for drinking. And understanding, and also water in the ocean as well. And understanding, the water cycle and the trends in the water cycle is very important for us to understand this resource and manage it for our use.
So you mentioned a number of different types of water we're tracking. Let's go into frozen water. Tell us about the ice sheets and the glaciers.
So ice sheets and glaciers are the largest freshwater resources on the planet. They took tens to hundreds of thousands of years to develop. They developed in places where the planet, where more precipitation or snow fell every year than was lost through melt during that year. And so snow and water, or snow accumulated there, accumulating this water resource. Now in this video clip here, this is an animation of GRACE data, and as Mike mentioned, about the trends around the globe. Here we can see in more detail how the GRACE data allows us to see how Greenland, one of the largest frozen ice reservoir that is melting right now, is evolving. We can see on a month-to-month basis the variations, the seasonal variations. We can see geographically where the changes are taking place, where it's draining from. And all this data helps scientists understand the forces which are driving the loss of ice from Greenland, the melting of water that is going into the oceans right now and contributing to sea level rise.
So from there, oh, there's more.
Oh yeah,
Sorry.
and so there's also in this clip here, this is similarly for Antarctica, you can see that we have monthly measurements from GRACE of how Antarctica is losing ice mass, and that's going to the oceans. And you can also see again the geographical distribution. You can see that in some parts of Antarctica are accumulating snow, and some are losing, particularly Western Antarctica. But the net effect is Antarctica is losing water mass, and that's going into the oceans. It's like 280 gigatons of water per year from Greenland and 120 gigatons of water per year from Antarctica.
What's a gigaton?
So a gigaton is a cube of water, a kilometer in size, and this graphic here just shows what that cube looks like sitting on Manhattan.
Wow.
It's equivalent to about 400,000 Olympic-sized swimming pools. And the ice mass loss from Greenland alone contributes to about a third of the sea level rise rate that we're seeing currently.
All right, so we just did the ice. Let's bring it a little closer to home. Can you tell us a little bit about the kind of water that people are relying on every day? What's going on with that?
Sure. So some of the trends that Mike showed in his chart were for not only ice but also for groundwater and groundwater depletion. And this animation here, video shows the loss of water mass in the western United States from 2003 to about 2013. And this was a period during some droughts in California and the western U.S. And you can see on a monthly basis we were able to sort of track how much water was stored in California and the western U.S. We can actually weigh it with the GRACE data, and you can see sort of the variations in the amount of water was there. Some years a little wetter, some years a little drier, and this allows us to track the water changes and help to establish the causes of the water scarcity in this region.
Thank you so much, Frank. Scientists have also put GRACE data to other uses that directly impact everyday life around the world. We're going to go now to Frank Flechner in Germany to talk about those, specifically flood monitoring and weather forecasting. Frank, can you start out telling us how you've been using using GRACE data for tracking floods?
Yes, of course, Karen. Flood forecasting systems require near real-time data to estimate the likeliness of flood events and to predict their evolution. Typical lead times for larger river basins are a few days, and challenging the conventional GRACE data processing for the application in risk and emergency management. Therefore, members of the European science team developed within a European Commission-funded project which was called European Gravity Service for Improved Emergency Management, gravity field solutions which are provided in near real time and with daily resolution. From these gravity solutions, we have then derived GRACE-based wetness indices. So if you start the video, you see that with this innovative data, we could track the generation and the development of historical flood events. For example, what is shown here, the April 2006 flood in the Danube Basin with a lead time of about 6 weeks compared to the river flow data at the outlet of the basin. And operational test runs were also performed between April and June 2017 within the German Space Agency Center for Satellite-Based Crisis Information. And it turned out that this near real-time data are really extremely useful for early warning. So if you look to the next slide, you see these GRACE-based wetness indices, which have been pre-operationally implemented in the global flood awareness system of the European Commission. In red, you can see drier, and in blue, wetter than normal conditions. So we are really trying to make a service out of the GRACE data.
And how will GRACE Follow-On continue helping with weather forecasts as well?
Yeah, so to explain this, please start the next video. So while the main global positioning system receivers on the top of the GRACE satellites were used for precise orbit determination, a set of secondary GPS antennas are at the backsides of the satellites and which are measuring the bending of the signals between GRACE and the GPS satellites that were low over the horizon. And this way the GPS signals graze and pass through the Earth's atmosphere, which is also known as the occultation. The GPS radio waves are altered slightly as they pass through the atmosphere due to refractive effects, and these changes can also be analyzed to create atmospheric profiles, including refractivity, temperature, or humidity, what you can see here on the slide left. CHEMP was a GFZ satellite launched in 2000 with objectives of gravity and magnetic field modeling and atmospheric sounding, so CHEMP can be seen as a precursor of GRACE. Since 2006, GFZ provides these temperature and humidity profiles operationally to various numerical weather services on a 24/7 basis, and an average delay of less than 2 hours to improve weather forecast. And to reach this stringent requirement of the weather services, we have also implemented a receiving station with 2 antennas in Spitsbergen near the North Pole, which you could see at the right of this plot, and which are able to download the occultation measurements nearly every orbit. And this station will also become the primary downlink station for GRACE follow-on. So one of the secondary objectives of the GRACE follow-on mission will be to derive at least 200 of these daily temperature and humidity profiles.
Thank you so much, Frank. That wraps up our discussion of the science of GRACE follow-on. Thank you so much to all of our experts here. We're now going to take your questions. Remember that if you are watching on NASA TV, all you have to do to ask a question via social media is to use the hashtag AskNASA. And with that, we have our first question from one of the media in our studio.
Hi, this is Paul Vusin from Science Magazine. I was wondering, originally GRACE and the GRACE follow-on were planned to overlap to aid in data calibration between them to get those long-term measures. And since they won't overlap, I'm wondering how you'll handle that.
Let me take a crack at that. So that is a good question. You always like overlap because you want to make sure that the measurements are not in some way biased in some unpredictable way, and that everything's consistent between the two measurement systems, particularly for things like long-term continuity. In the case of GRACE and GRACE follow-on, the measurement, because it's a change measurement, it doesn't lend itself to being biased in the way many conventional measurements are. So the requirement for overlap is less critical than it might be for some other types of missions. GRACE is really measuring the derivative of things, how fast things are changing. And it's not the absolute amount of water, but really the change. And that's something that's harder to be biased. But we want to double check anyway. And the way we double check is by looking at other satellites less precise than GRACE that have been observed in the gravity field at very, very long wavelength, very coarse spatial scales. So they can kind of see, yes, Greenland was doing about this, or Antarctica was doing about that, or there were large-scale changes in the northern hemisphere or southern hemisphere due to water storage. And we can compare those and make sure that when you interpolate the last GRACE data point, those intermediate course points and the first GRACE follow-on point, that those all look consistent. So we believe it will be satisfactory to have this fairly short gap of about a year, year and a half.
All right, we have another question from the room.
Randy Shostak, reporter with EOS at the American Geophysical Union. Thanks very much for doing this briefing. I wonder if you could just tell me what, in your estimation, is the most startling, the most important findings that you've gotten from GRACE, and what are your biggest hopes from GRACE follow-on?
So I'll say from GRACE, I think the rate at which the polar caps were losing mass was something that was a little surprising to folks. You know, when we launched GRACE, it wasn't clear how fast the polar sheets were changing. I think GRACE gave the first clear picture of what's going on, and of course that's been followed up with other more precise measurements for local areas, like with radar or the upcoming ISAT-2 mission. But I think generally understanding how the polar caps are evolving is probably the biggest surprise from GRACE, along with just the clarity that GRACE gave for the hydrological basins around the world for groundwater. And Frank, you want to talk about GRACE follow-on?
Yeah, and well, let me just add to that, Mike. And, to me, one of the more interesting and exciting things was, the understanding of how when the ice caps are melting and they're contributing mass to the oceans, but in 2010 or 11 there was a slight kind of dip in the rate of rise, actually reversal in the rate of rise of sea level, and that was related to more water being stored on land. And so we could see mass was being lost from the ice caps and the ice sheets, Greenland, Antarctica, going, but it wasn't all going to the ocean. Some of it was getting stored on land and was later released, through just normal processes for water running off land.
I think one thing that's important to follow up on that is the fact that GRACE observes what happens in many components of the hydrological cycle allows you to actually answer the question, water left here, where did it go? And in the case for that Frank's talking about, or other cases, we actually see it go from one place and show up somewhere else. And that allows scientists to really try to unfold exactly how water is transported, at what rate, and what are the most important processes that govern the water cycle on the Earth.
Yeah.
All right, we now have some questions from social media.
A user on Twitter has the following question. If the GRACE follow-on mission can measure water underground, does that mean it can also find and track new underground lakes and rivers?
It can. So the first thing to remember always about GRACE is that it senses the change in water and not the absolute content of water. So it doesn't tell you you have 10 feet of water in that well. It tells you you used 10 feet of water since last month. So in areas where the aquifers are varying quite a bit, it is possible to actually go and look for areas of water storage or water depletion that have not currently been known. And there actually have been a few aquifers found using various techniques, in parts of the world that are not widely used for irrigation and not widely used, do not have a lot of wells in them already.
We have another question from social media now.
Trisha Patterson would like to know, how and when will data from this mission be shared with the public? Is there an option for ongoing sharing of the findings?
So the mission will be shared immediately as soon as we get it and analyze it. So the mission launches, and we have about a 90-day period of checkout. And then during that period, we'll be collecting data. We'll be collecting gravity data. We'll be making sure the instruments are working and everything's operating well. And then shortly after that, we'll start releasing, maybe 120 days after the initial checkout, our first data products. And that will then, you'll be able to add those to the existing sort of database of GRACE data and move forward. So it'll all be, freely available, publicly available as soon as, 120 days or so after launch.
Thank you. We have one last question coming in from social media.
Twitter user Jamie Meyer wants to know which rocket will launch GRACE follow-on.
Right. So GRACE follow-on is being launched on a Falcon 9 from Vandenberg on May 19th is the scheduled date. It's part of a ride share with Iridium Communications. So we'll be riding along with 5 of their satellites, and then we'll be released first, and then they will go into their orbit and release their satellites.
We're going to talk quite a bit more about that in the second part of this briefing.
We had some great questions. Thank you so much. Now we're going to switch gears. We're going to start talking about the twin spacecraft themselves and how they work. We're also going to take a look at launch preparations in California. So stay with us. We'll be back in just a minute. We are back with more on the GRACE follow-on mission, which as we speak is currently at Vandenberg Air Force Base in California, getting ready for a launch on May 19th. Here with us to talk about the spacecraft and mission operations are David Jarrett, who is the GRACE follow-on program executive in the Earth Science Division at NASA headquarters. We have Phil Morton, the GRACE follow-on project manager at JPL. And again, joining us from Germany via Skype, we have Frank Flexner, who is the GRACE follow-on project manager at the German Research Center for Geosciences. So Dave, let's start with you. I understand that GRACE follow-on is really very different from the typical Earth observing spacecraft that we have. Can you tell us a little bit about how it compares to some of the other things in NASA's science fleet?
That's right, Karen. We have a variety of Earth observing satellites circling the Earth right now that are measuring different aspects of the Earth, from particles circling the Earth to land masses to even the clouds that are circling the planet. If you go to take a look at this animation here, you can see that NASA currently has about 17 different satellites orbiting the Earth in many different orbits. Most of these satellites are in low Earth orbit, and they generally measure things in certain ways. If you could go to the next graphic. The two ways that these spacecraft measure different characteristics are a passive way, which acts like a camera and collects the reflected light off of the planet, and then the instruments break these down into various wavelengths that are then analyzed for the different characteristics that we're looking for. Second type of instrument is an active instrument like radar or LIDAR that sends out an active pulse or an active laser pulse that then bounces back off of whatever particle it reflects off of, and then that beam is analyzed for different characteristics. Unlike these two ways of collecting data, GRACE follow-on is not your average everyday Earth science type of mission. Spacecraft don't essentially see anything on the ground or measure anything on the ground. The two spacecraft are actually the science instrument when you combine them. As can be seen in this video here, the way the major measurement or prime measurement of the GRACE follow-on mission is a very precise measurement of the distance between the two satellites. And as the satellites pass over different portions of the Earth, the distance between the satellites change based on the pull of gravity below them. For instance, when the first spacecraft passes over a mountain range, such as the Himalayas, it'll speed up slightly and increase the distance between the two satellites. As the second satellite approaches the same mountain range, it too will increase speed and therefore decrease the space between the two satellites. And this goes on and on as both satellites orbit the Earth. And from this data, scientists can then estimate the gravity field to great precision for the entire planet.
Thank you very much. Now let's go to Phil. Can you step us through the kinds of things Dave was telling us about? Tell us exactly how GRACE follow-on does its work and what are the key components?
Sure, Karen. We brought these models to show you the various pieces and parts of the satellite on the outside. On the front end here, you can see the microwave instrument antenna. These are the two antennas that the two spacecraft point at each other. They use two microwave frequencies to measure the distance between the two spacecraft. They fly about 137 miles apart. At that kind of a distance, we can measure distance changes about the thickness of a blood cell. You can also see two ports here. These are baffles for the laser ranging interferometer. This is a technology demonstration instrument that we've added to GRACE follow-on. And there we'll use a laser beam bouncing between the two satellites to essentially accomplish the same measurement as the microwave, but more accurately. Some other things to notice about the spacecraft: solar arrays on the top, and the two sides give us the power that we need. These cutouts here, they're on the top, and the two sides are for our star camera baffles. We use 3 star cameras to map our location in space as we're flying and taking these measurements. We also have on top a precision GPS antenna, and we use GPS data to also map the distance changes relative to Earth. And then finally on the back side, you can see the GPS occultation antenna that Frank was talking about earlier. This we use to look at GPS signals as they rise and set over the horizon to measure moisture in the atmosphere.
And how do you put a complex spacecraft like this together?
Well, it is complicated. We have a video here. You can see this is film of the spacecraft being assembled at Airbus. Airbus is located in southern Germany, in Friedrichshafen. They are our primary contractor for the build of the 2 satellites. It's quite compact inside. You can see the fuel tanks, the solar arrays being added here. One of the challenges we had was integrating the laser ranging interferometer into the system as it stood for GRACE, or as it was done on GRACE. Here's a shot of the accelerometer. This is a key component inside the spacecraft. Very carefully aligned with the triple mirror assembly, part of the laser instrument. Also the star cameras, so the optical alignments are very critical. And then you can see the whole unit being dropped down into the very heart of the spacecraft. These alignments are critical, so critical, they're done first, and then we align the rest of the instruments to those, make sure everything's properly and mechanically aligned.
Thank you so much, Phil. We are going to turn back now to Frank Flechner in Germany. Phil just explained that there's a new technology demonstration instrument that wasn't on the first GRACE mission. Frank, can you tell us more about that, and what do you hope to achieve with it?
Yeah, sure. So on the next image, you can see a sketch of a laser ranging interferometer. As you have heard in Phil's overview, it was a real challenge to implement another instrument into the already fully equipped satellite. The laser ranging interferometer is a technology demonstrator for future next generation gravity missions to improve the accuracy of the inter-satellite ranging. It is important to mention that the success of GRACE follow-on will not rely on this technology demonstrator. If it should not work as planned, the gravity field modeling will be based on the microwave instrument only, and GRACE follow-on will still be successful. The laser ranging interferometer is an excellent example, to my opinion, of a cooperative project with a great partnership. The US focuses on the electronics, the cavity, and the procurement of the laser from Germany. And Germany is focusing on the optical parts, for example, the optical bench or the triple mirror assembly. On the optical bench assembly, the received beam from the distant spacecraft is inferred with a small fraction of a local oscillator beam. The larger fraction of the local oscillator beam is retroreflected by a triple mirror assembly and sent back to the distant spacecraft. The assembly consists of 3 perpendicular mirrors mounted into a rigid structure and works like a corner cube reflector. The cavity is used for frequency stabilization of a laser, and with all these components implemented on both satellites, as a so-called racetrack configuration is established between the satellite. And the inter-satellite range is continuously measured with a precision of about 80 nanometer, which is twice the size of a hepatitis B virus over a distance of Los Angeles to San Diego, for example. So on the next slide, you see top left laser retroreflectors, which have been provided by GFZ and which are mounted on the bottom of each of the 2 satellites. We use a network of about 20 ground stations which send a laser beam to the retroreflector. On the bottom right, you see as an example the GFZ station in Potsdam, Germany. By comparing the time delay when the signal was sent and again received at the laser station, the two-way range can be obtained with millimeter precision. This serves for an independent control of a GPS-derived orbit.
Now, in addition to the important science it will do and the technology it uses, we're excited here at NASA about GRACE Follow-On for other reasons too. The mission marks the continuation of a major U.S.-German collaboration. Dave, can you talk a little bit about that collaboration and tell us in general what these kinds of international partnerships bring to NASA?
Absolutely. NASA has been working for many, many years with our international partners in collaboration to conduct Earth science measurements. It is indeed a global effort, and the data is very important to everyone around the world. As this graphic shows here, we have several missions both on orbit and in development in cooperation with our many international partners. Part of the reason for international collaboration is to be able to reduce the costs for each contributing country. For instance, for GRACE Follow-On, we're working with GFZ on this. We worked on GRACE, the original GRACE, with the German Space Agency. And what we both get out of this essentially is more bang for the buck, and euro in this case, for the investments that these different countries have made. For the gravity measurements, we've been working with Germany since the 1990s, first on the GRACE mission starting in 1998, and now continuing this successful partnership with GFZ, with Frank Fleckner as the lead of the German side with their contributions. Together, we look forward to a very good mission. As Frank Fleckner had said earlier, the Germans are contributing the launch, mission operations, the optics of the laser ranging interferometer, and the laser retroreflectors. The U.S. is providing overall project management, the two spacecraft, the accelerometers, and that's about it.
Wonderful. Thank you so much, Dave. Let's hear from the German side, too. We're going to go again to Frank to hear about the partnership from the German perspective.
Yeah, so GFZ has a long tradition in gravity field determination. For example, GFZ has built and operated CHAMP, the CHAMP satellite in 2000, which was a kind of precursor of GRACE. With first-time continuous high-low satellite-to-satellite tracking between CHAMP and the GPS satellites, and for the very first time flown an accelerometer for gravity field improvement. The collaboration in the US-German science data system and between the US and European science data teams helps GFZ to improve gravity field and Earth system modeling expertise. The technology demonstrator of the laser ranging interferometer will enable German Space Agency DLR and German industry to prepare for next generation gravity field missions. And it's also a win-win situation for the German taxpayer, as the cost for the German contributed items like the LI, the science data system, the launch or mission operations are all refunded as the twin GRACE follow-on satellites have been bought by GPL from Airbus in Germany.
Thank you very much. Now it's time to focus on an essential part of any space mission, the launch. And of course, after that comes the mission operations to maintain the spacecraft once it's on orbit and doing its work. So Frank, can you step us through these key elements?
Yes, of course. So GFZ has signed a rideshare contract with Iridium to launch the GRACE follow-on together with 5 Iridium Next satellites on a SpaceX provided Falcon 9 rocket. So could you please start the videos to explain it a little bit? So the launch site is Vandenberg Air Force Base in California. As mentioned before by Frank Webb, The current target launch date is May 19. So 707 seconds after liftoff, a separation system will fire Pyrus to deploy the twin GRACE follow-on satellites in a nearly the same nominal orbit at 490 kilometers and 89 degrees inclination. The separation impulses will push the two spacecraft in opposite directions. The Vandenberg Air Force Base will confirm a successful separation using downlink telemetry data from the upper stage. So less than a minute later, a boom that holds each satellite's radio frequency S-band antenna is deployed and the low-rate radio transmitter is activated. The first data from the spacecraft are expected about 23 minutes later to be received through the first pass over NASA's tracking station at McMurdo at Antarctica. And to talk about mission operations, please start the next video. So for these activities, GFZ has subcontracted for the nominal mission lifetime of 5 years with German Space Operations Center of the German Space Agency. As for GRACE, the German Space Operations Center is providing the ground data system to monitor and control the satellites, perform initial processing of the telemetry data, and to deliver all the data to the science data system for further processing and generation of science products.
So Phil, can you tell us a bit more about launch preparations right now at Vandenberg?
Absolutely. After we continued or finished up our environmental testing just outside of Munich at a test facility there called IABG, we loaded all of our equipment, transported to Vandenberg Air Force Base. I have a video here that shows the arrival. When we landed, we got help from the U.S. Air Force to unload all of our equipment. That equipment included the 2 satellites, our multi-satellite launch dispenser, all the ground support equipment. We trucked everything over to a facility called Astratech, and there we do a full checkout, completed a full checkout of the 2 satellites, made sure everything survived the transportation, and everything was working perfectly. We fuel the satellites and then get them ready, mounted them on our launch dispenser, and then we've transported the entire combination of the 2 satellites and the launch dispenser, what we call the stack, the GRACE-FO stack, over to SpaceX, where we've been waiting to do integration with Iridium and with SpaceX. Those activities are scheduled to start up this week, coming the end of the week here. So we're very excited about this and getting very close to launch.
It is exciting. Let's keep going. What happens once it launches? When can we expect science?
So as Frank spoke of, once we finish that first pass over McMurdo, we start our 90-minute polar orbits. The Earth is rotating underneath us. We focus the first few days with North Polar and South Polar stations to get the maximum amount of data that we can. We do about 5 days of checkout on all of the avionics and the science instruments themselves. Then we go into a commissioning phase where we get the instruments up and running. We do calibrations. We verify our very first gravity fields, make sure the quality of everything is working well, do any fine-tuning that we need. And then we'll go into our science operations phase at about 90 days after launch.
Fantastic. Thank you so much to all of our experts here today. We are now ready to take some more questions. Again, if you are watching on NASA TV, you can ask a question via social media with the hashtag AskNASA. And our first question will be from the studio.
Paul Vusin from Science again. If the laser ranging works as hoped, what types of mass changes might you be able to detect that the original GRACE did not?
Oh, that might be a good question for Mike Watkins to answer.
Mike can take a crack at that. So first of all, as Frank Fleckner noted, the laser is kind of a demonstration that we can make this kind of measurement. It's a very complicated measurement to make. It's a very precise measurement. It's never been done in space before between two spacecraft, certainly anywhere near this precision. So we want to really just make sure we can actually make this measurement and that we understand the measurement. If it works, it could be up to several times better than the microwave measurement in terms of accuracy. It could be as much as maybe 10 times better, or even a little bit more, depending on exactly how the system performs. So if that continues to work, we will produce gravity fields from the laser and from the microwave system until the laser stops functioning. So we intend to actually go ahead and produce those science products if the system is all working, but the baseline for continuity to continue the 15 years is really the identical system for GRACE, the micro system. But as long as the laser is working, we will analyze those and produce them. Although the ranging measurement is more accurate, the resolution of the physical phenomenon on the Earth may not be anywhere near. It's not a linear relationship. So if the laser measurement is 2 times better, you might only get 10% better spatial resolution, because there's a lot of other factors that go into it, how the drag is measured and other technologies. But if the laser is successful, then that means future missions we could have a more accurate mission.
We have one more question from the studio, from the press.
Randy Shostak again with EOS. Is the addition of the laser ranging interferometer the only significant difference between GRACE and the follow-on?
I'll take a crack at that. It is a very significant difference to add it, but we also took advantage of lessons learned from the GRACE mission, and we fine-tuned some of the construction techniques that were used on the spacecraft to eliminate noise, background noise. And then because of the time frame between GRACE and GRACE follow-on, we've had to include more advanced avionics and things. So there have been a number of improvements inside the spacecraft. It was a real challenge to keep the outside of the spacecraft looking very much the same size as GRACE, flying the same way. But inside we've made adjustments as we needed to make sure that we have the kind of mission that we want.
We also have some questions from social media.
A user watching via Space TV asked, why is GRACE follow-on the shape that it is? Can you explain that for us?
Sure, I'll take a crack at this. It's the aerodynamics. It's a combination of the aerodynamics of the body, which allow it to do the kind of mission that we do without being influenced too heavily by other effects in space. But also we have a very tightly controlled thermal control system inside, and we monitor very closely and control the temperature of all the elements inside so that we make sure we don't have any influence from flying in and out of the sun, for instance, that would affect the gravity field measurement itself.
Okay,
we have another question.
Yes, there's so much excitement on social media related to this topic. On YouTube, Gunny asks, will the GRACE follow-on launch and deployment be shown live? And if so, how can he watch it?
It will be shown live. I think it'll be
NASA.gov/NASA TV is definitely one place where you'll be able to see it. Great. We have no more questions at this point, so that concludes our briefing for today. Thanks to everyone who has been watching. If you'd like to learn more about the GRACE follow-on mission, go to nasa.gov/GRACEFO, and don't miss the launch. Mark your calendars for May 19th. Thank you very much.